Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 4 on point reflections. So for the past few lessons we've been looking at rigid body motions and specifically looking at rotations. Today we're going to look at a very special type of a rotation which weirdly enough we're going to call a point reflection. And we'll kind of talk about why we call it a point reflection in a bit. But let's get right into it and talk about what these things are. Point reflections. One important type of transformation is known as a point reflection, which is just a very special type of rotation. So let's talk about what a point reflection is. A point reflection is a rotation of points in the plane about a given point by exactly 180 degrees. Since it is exactly 1/2 of a full rotation, the direction of the rotation does not matter. All right? So point reflections are 180 degree rotations. And those are kind of almost the nicest rotations out there, all right? And we'll take a look at why that is in exercise number 1. Let's take a look. Using a straight edge and compass only, find the image of segment AB after a point reflection across or through point C. Again, this is the same as a rotation about point C by 180 degrees. Now, remember, right, all rotations are this idea, and I'm going to do a quick hand sketch, don't do this yet. All rotations are this idea that, okay, if I rotate point A, forget about point B for a second. If I rotate A about point C, right, what I'm doing is I'm moving it along a circle. So it's always saying the same distance away from C as what it started, right? Now, because it's 180 degrees, right, the idea would be that the angle that it would make, and we'll do this like for real in a moment, the angle that it will make will be a 180 degree angle, which means that these 3 points, the pre-image point, the center of rotation, and the image point will all be collinear. They will fall in a straight line with A being the same distance from C as A prime, or better yet, I should say A prime is the same distance from C that A was when it started. So let's see how to do this with only a compass and a ruler, all right? And it's really quite cool, but it rests on the idea that you understand that the point, the pre-image point, and its image point will be collinear. So what I'm going to do is I'm going to draw a lengthy line segment through A and through the center of rotation, all right? Now, I'm not going to use my ruler to measure this length. What I'm going to do is I'm going to take my compass out and I'm going to put the point of the compass at point C. All right, and I'm going to extend the compass out so that it gets to point A, and then I'm going to put the point of the compass back on C. All right, I want to get that exactly or as close as I can to point A. And then I'm going to make a little arc. Now I can make a larger arc, but all I'm really trying to do is measure the distance from C to A using my compass. Then I'm going to reverse the orientation and measure that same distance. And that now, that now must be the location of point A prime, right? It must be the location because those 3 points, A, C, and A prime are collinear, and I have guaranteed that CA and CA prime are the same length. What I'd like you to now do is figure out where B gets mapped to and then draw in segment A prime, B prime. Go ahead and do that. All right, let's do it. I'm going to make my ruler a little bit shorter for the moment. Bring this up. Again, I want to line B and C up because wherever B prime is, it's somewhere along this line segment. All right, so I'll draw a nice long line segment. It just has to be longer than the segment length BC. All right, bring this up, give myself a little bit more electronic room. Flip it around, come up. I want to get that right as close as I can to B. Hopefully you'll be able to get it right on the mark. I'm having a hard time doing it, but we're going to make that little mark. bring, whoop, oh, really? I really just lost that, didn't I? All right, that's okay. Somehow I just got rid of that other segment. We'll grab it in a moment. There it is. All right, and then we'll get rid of our compass. Where'd that thing go? And here is B prime. Yeah, why don't you come back here? There we go. And that should be the final picture. I now want to draw in segment A prime, B prime. Just segment A prime, B prime, not line A prime, B prime. Just the segment, and there it is. Oh, man. There we go. So, very, very simple. But of course, it relies on you knowing that when you rotate a point about another point by 180 degrees, those 3 points end up being collinear. That's really key. And it's really what makes a point reflection sort of special, or a rotation by 180 degrees special. Now, the reason it's called a point reflection is that, and we're going to talk a lot more about line reflections in coming lessons, but a reflection generally is, right? Oh, if I look at myself in a mirror, a reflection, which I do, I don't know, like 30 or 40 times a day, then what happens is, my reflection is the same distance from sort of the mirror as I am. So the idea is that B prime is the same distance from C as B is, and A prime is the same distance from C as A is, right? And in the same direction. And that direction being that 180 degree kind of like line that we've got there. Now, we don't want to forget about answering this little side question. What must be true about the lengths of segment AB and segment A prime, B prime, Y? Well, they must be the same length, right? Must be the same length. Oops, length, not with a B, but with an H, because a point reflection is a rigid motion. Right? And of course, the reason it's a rigid motion is because rotations are rigid motions and point reflections are just 180 degree rotations. I really wish we would just call them 180 degree rotations, but they want you to know that a 180 degree rotation about a point is called a point reflection. Awesome. Let's keep going on. All right. After a point reflection occurs, the image point is the same distance from the center point as the pre-image, and all 3 points are collinear, right? That's the real key on all of these. Now, last time we did a point reflection of a segment. Now let's do a point reflection of an entire triangle. Exercise number 2. Using a straight edge and compass only, construct the image of triangle EFG after a point reflection across point M. Leave all construction marks. Label the image triangle E prime, F prime, G prime. All right, this diagram is definitely going to get a little busy looking. Let's do point E together and then have you do point F and point G on your own. So again, I'm going to just bring my straight edge up. I'm going to draw a line segment that passes through E and M. All right, and I want to make it long enough that then it's going to have E prime on it. Okay, I think I have to actually maybe bring this thing upside down. Okay, I'm going to put my pointy end there. Bring this out, rotate it up a little bit closer. Oh, perfect, perfect, perfect. I need to draw that little arc, or maybe not so perfect. Then I'm going to draw this, oh, come on. This little arc, and that, hopefully, is going to be point E prime. Okay. Now what I'd like you to do is do exactly the same things with point F and G. Once you have F prime and G prime, then connect all 3 of them to form triangle E prime, F prime, G prime. Go ahead and do that. All right, let's do it. I think I'll do F next. Again, here comes my straight edge. Let's get that a little bit better lined up. Excellent. All the way through. Get rid of my ruler for the moment. Bring this up. Come on. There we go. Stretch it out. Rotate. Move my ruler somewhere else. Bring it back. All this inner monologue you've got to hear, obviously, from me. And now let's find out where the point is over here. Great. So that's going to be F prime. And then finally for G, same song, third verse. All right, we're gonna have to stretch my ruler out a bit. All right, not sure where G prime is, but it's somewhere up there. Rotate this down, maybe a little bit like this. Flip it, open it up, get that distance right. So many things in the way. Ah, there it is, not bad. Okay, there's my distance. And find it up here. Thankfully, I can now put that bad boy away. That is going to be point G prime. And I can now draw in my triangle. I do this with my straight edge because I want to make it look good. There. There. And, oops. Bring this up here. Sorry, these always take some time. There. All right. And there is that point reflection. Looks cool. It's a little bit hard to tell, but hopefully you can kind of get a sense that this triangle, E prime, F prime, G prime, is identical to this triangle. It's just been rotated 180 degrees about that point. All right, and that's it, right? It kind of looks the way it would look if there was somehow a zero-dimensional mirror sitting there. That didn't make any sense. All right, let's keep going and looking at more issues having to do with point reflections. Now, just like we can do point reflections in the Euclidean plane if we're given a straight edge and a compass, we can also do point reflections in the coordinate plane. All right, the most common is to reflect across the origin, and you'll like these. These are awfully easy to do. Even with my problems plotting points, I think I might be able to pull it out. Exercise number 3. Triangle MNO with vertices at M 1, 4, N 4, 6, and O 8, 2 is graphed. Yeah, I rearranged that sentence a little bit. That's okay. Letter A. Draw the image of triangle MNO after a reflection across the origin. Label its image M prime, N prime, O prime. Show the mapping below. All right, well, how are we supposed to figure out where each one of these points goes? Well, let's play around with this just a little bit for a moment. I'm going to take my ruler and sort of do exactly what we did before, okay? I'm going to put it on M. I'm going to rotate it so that it goes through the origin, hopefully so that it goes through the origin. All right, and I'm going to just kind of draw out, really? I'm going to just sort of draw that line out. Now we know, right? We know that somewhere along that line M prime has to lie. Now right now M prime lies 1 unit to the right and 4 units up from the origin. If I want it to lie exactly the same distance from the origin, its image to lie exactly the same distance from the origin that the original point did, the pre-image point, then I should go 1 to the left and 4 down, right? And I'll end up having an image right here. I did not do the greatest job drawing that original line. So I'm going to just delete that. So I should have a point right here. So in other words, M, which is at 1, 4, should go to M prime, which is at -1, -4. And in fact, one of the beautiful things about point reflections is that the pattern that we see here is going to occur again and again, which is that x, y is simply going to go to -x, -y. right? And think about it for a minute, right? Here I've got point N, right? It's at 4, 6, right? So if I was thinking about how to go from N down to the origin, I would go 6 units down and 4 units to the right. Then if I want it to be collinear, I'll go another 6 units down, another 4 units to the left. Sorry if I said right before. And it would be somewhere down here. Specifically, right, N, which is at 4, 6, will then go to N prime, which is at -4, -6. Right? And finally, O, which is at 8, 2, will go to O prime, -8, -2. And again, I'm just going to terribly sketch my triangle in there. That doesn't even look remotely close to being a straight line segment, but there we go, right? And the rule is so simple. It's not so simple if you're not reflecting in the origin. If you're reflecting in some other point, it's a little bit more challenging. But in the origin, it's fairly easy. F of x comma y simply goes to -x comma -y. All right? And it should sort of make some sense, right? What's happening here is that keeps us on the exact same line and the exact same distance from the origin that the original point started from. All right? And again, you can see how this looks very similar to that picture in the last problem. The big difference is this isn't located on a coordinate grid, whereas that is. Simple enough. All right, let's take a look at exercise number 4. A company is designing a logo for a new app that they're marketing. Half the logo is shown below. The other half will be the image of the portion shown after a point reflection through the origin. Complete the logo's design, shade appropriately. Show how vertex points on the design are mapped under this point reflection. All right, so let's do a few of these together. For instance, if I took this point, right, that's at -6, +6. Maybe that wasn't the best point to start with, but -6, +6, right, if I change the sign on both of these, will become 6, -6. So it's going to end up being down here. I haven't labeled any of these A, B, C, D, or anything like that, so I'm not going to here. All right, but I want to do that to, let me get that arrow off of there. I want to do that to this point, to this point, to this point, and we'll talk about the origin in just a moment. But why don't you go ahead and do that? You know, carve out each one of those points, plot it, draw out the figure, and shade appropriately. All right, well, why don't we do this one next? That's at the point -9, -4. So -9, -4 will become the point +9, +4. +9, +4. All right, this point, which is at -5, +2, will get mapped to the point +5, -2. Okay? And finally, the origin, right, which is right here, 0, 0, I suppose would go to -0, -0, but that's just the same as 0, 0. Kind of makes sense that the point of reflection, right, the center of the point of reflection wouldn't go anywhere if you reflected it in it, because it's 0 distance away from that point, so it just kind of stays there. So we end up just kind of getting this point, right, and again, kind of free form, we end up getting that, right? And it's got this cool symmetry, right? If we rotated this entire thing, which I'm not going to even attempt to do right now, right, this would end up landing here, and this would end up landing here, which could be a cool logo, you know what I mean? I could do that as a logo. All right. Now, there's a few more issues that we have to look at with point reflection, specifically what happens when we do a point reflection on an entire line, okay? When lines are transformed using point reflections, interesting things happen, and we have to look at two distinct cases, and these are going to be very important moving forward. So let's kind of take a look at them one at a time. Exercise number 5. Line AB is shown below, which contains point C. Consider rotating AB by 180 degrees about point C. Let me move that compass off of there so you can see it better. Letter A, use a compass to locate the image points A prime, B prime. Letter B, what can you say about the two lines, line AB and line A prime, B prime? So this is interesting. So this gets into a very basic issue. If I have a line and a point on that line, and I rotate the line 180 degrees about that point, what happens to it? Well, with all point reflections, right? Like let's say I wanted to reflect point A through point C. Well, what I would do is I'd draw a line from point A through point C, and I would just locate A somewhere on the other side of it. So in other words, and let me kind of do this so I can get to it. All right. Okay, close enough. Ooh, actually right on the money. Right, this has got to be where point A is. Or sorry, where point A prime is, where point A gets mapped. Okay, why don't you go ahead and figure out where point B gets mapped? Okay, very similar. Let's bring this up here. Man, what I wouldn't give to just have a normal compass and normal paper right now. All right, that's, again, more or less where I want it. Not quite, but I can only get so close on here. Hopefully yours is a little more accurate. Splits. Nope, it's just not going to go away. There we go. There's point B prime. There we go. So letter B, what can you say about lines AB and line A prime, B prime? Pause the video now and write something down. All right, well, they're the same line. And by the same line, they are the same line. And by the same line, I literally mean they are the same points in space, right? And that kind of makes complete sense. If I've got a line and I rotate it 180 degrees about a point that lies on that same line, it's just the same line, right? That's not true of any other rotation, right? But a 180 degree rotation, a point reflection about a point that lies on a line, will leave the line unchanged or wherever. Anyway, now let's look at the other issue. Okay, exercise number 6. Consider line AB shown, which does not contain point C. Using a straight edge and compass, find the image of line AB after a 180 degree rotation about point C. All right, so what I'd like you to do is, figure out where point A prime goes, somewhere down here, point B prime, somewhere down here, and then draw that line that passes through AB. Go ahead and do that. All right, this is going to take a little bit longer, obviously. So first things first, I've got to draw that line that goes through A and the center of rotation. All right, then I need to use my compass. Maybe now I have a little bit more room here to play with. All right, that works. And there's A prime. All right, let's now do the same thing with B. Actually, I guess I got to do it like this. I think I need to extend this a little bit. Oops. All right, Now let's bring our compass back in. That was not the best shot there, but that's okay. I'll actually do this. Come on. There we go. Let's bring this out and yeah, that's good. And now just switcheroo. There it is. That is one thing I like about the electronic compass. I can flip it very quickly. B prime, and finally, after all of that, I can finally draw, I knew that was going to be the case, line B prime, A prime. Yeah, okay. There it is. There is line A prime, B prime. Okay. So in the first case, we rotated or point reflected a line through a point that lied on the line. In this case, we point reflected a line through a point that doesn't lie on the line. Great, wonderful. Now, letter B, what appears to be true about line AB and line A prime, B prime? What appears to be true? Go ahead and try to answer this. Pause the video now. Well, they hopefully appear to be parallel. And we will eventually take a look at why that is. It's actually an amazingly important property of point reflections. Very important property of point reflections. And you can kind of tell it a little bit if I take my ruler up, and try to line it up here. Oh my goodness. Okay. Make it parallel with that line. Then I can bring it up here, and it should be parallel, even if it's not quite. That's inaccuracy on my own point reflections, but they're parallel. All right? And that's an amazingly important idea, that when you have a line and you point reflect it through a point that's not on the line, then the resulting image line is parallel to the original one. All right. Let's move on. One last problem. Rotation by lines by 180. When a line is rotated by 180 degrees about a point not on it, the image line produced is parallel to the original line. Exercise number 7. In the diagram shown, triangle CDM is the image of triangle ABM after a 180 degree rotation about point M. And again, I could have said after a point reflection through point M or across point M. Letter A. What two line segments must be parallel based on this information? Well, there's pretty much only two line segments that look parallel in here, but, right, keep in mind that M lies on segment AM and M lies on segment BM, right? But M does not lie on segment AB. So when AB is rotated by 180 degrees around point M, it becomes CD. So AB must be parallel to CD. All right. You can mark parallel line segments with little arrows, kind of like this. That's got to be parallel to that. All right. Letter B. Why can you say that triangle CDM is congruent to triangle ABM? Okay, well, this is simple enough. Rotations are rigid motions. And so triangle CDM must be identical to triangle ABM. Rotations, in fact, you can just say rotations are rigid motions. Now, letter C, label the two angles in this diagram that must also be 56 degrees and 81 degrees. Remember, rotations and rigid motions in general don't alter the size of angles. So the angles in the image should be the angles of the original. Pause the video now and write down two angles that are 56 degrees and 81 degrees. Well, again, think about it. If I took B and I rotated it 180 degrees, it would be up at D. And therefore, if that's a 56-degree angle, this is a 56-degree angle, and likewise, that must be an 81-degree angle. All right? And by the way, you should now kind of see some things about parallel lines here. That 81 degrees and that 81 degrees are alternate interior angles, as are that 56 degrees and that 56 degrees. So we're already kind of seeing those angle properties that occur when we have parallel lines. All right, let's wrap this up. So today we looked at a very specific type of rotation, which then for some reason gets the word reflection, right? A rotation around a point or about a point by 180 degrees is known as a point reflection. And these are so special because the pre-image point, the center of rotation or center of reflection, and the image point are all collinear. And so we can actually create these types of point reflections / 180 degree rotations in the Euclidean plane if we're given a straight edge and we're given a compass. Now, in the coordinate grid, it's super easy because as long as we're reflecting through the origin, all we have to do is take our xy pair and change the sign on both x and y. We don't have to flip x and y or anything like that, like how we had to do with the rotations. All we have to do is change the sign on both x and y, and that will be where the image point lies. At the end, we saw two important ideas. The idea that if you rotate a line about a point on the line, then you just get the same line, as long as you're rotating 180 degrees. But if you rotate a line by 180 degrees about a point not on the line, you produce an image line that is parallel to it. And again, that's going to be important and have important ramifications. All right, for now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.